Hi friends, this is Rashekar, a GATE faculty for electrical machines. In this video, we are going to discuss about the previous GATE question. In this video, see the question. A single phase air core transformer fed from a rated sinusoidal supply is operating at no load. The steady state magnetizing current drawn by the transformer from the supply will have drawn by the transformer from the supply will have. This is an air core transformer. There is no non-linearity. There is no non-linearity. For air core transformer, magnetizing current is sinusoidal and flux is also sinusoidal and EMF also sinusoidal. For air core transformer, even though I mu is sinusoidal, the flux also sinusoidal and EMF also sinusoidal. So here the answer is sinusoidal waveform only. The magnetizing current is sinusoidal waveform only. There is no non-linearity for air core transformer. This is simply about the concept of non-linearity. Right? Are you okay? See a problem on OC and SC test. Listen carefully. A single phase transformer has no load loss of 64 watts is obtained from an OC test. No load losses obtained from an OC test. When SC test performed on it with 90% of rated current, nothing but at 90% of load, 90% of rated current, following in both LV and HV winding, 90% of rated current flowing in both LV and HV windings. The measured loss is 81 watts. Nothing but these are the copper losses. These are the copper losses at 90% of load. The transformer has maximum efficiency when operated at. They want the load. At what load we can get the maximum efficiency? What is the formula? At what load we can get the maximum efficiency? X is equals to square root of iron losses upon copper losses at full load. Iron losses upon copper losses at full load. At that load condition, we can get the maximum efficiency. And iron losses, they given that core losses are iron losses are no load losses are 64 watts. Now we want full load copper losses. What is the formula? Xth load copper losses is equals to X square times of full load copper losses. Xth load copper losses is equals to X square times of full load copper losses. Here 90% of load copper losses is equals to 90% whole square into full load copper losses. We want full load copper losses. We know the 90% of load copper losses. They given 90% of load copper losses 81 watts. So substitute here. This is 81 is equals to 9 square 81, 10 square 100 into full load copper losses. 81 cancelled. So full load copper losses is equals to 100 watts. Full load copper losses is equals to 100 watts and iron losses is equals to 64 watts. Then at what load we can get the maximum efficiency? Square root of iron losses upon copper losses, root of 64 8 and root of 110, nothing but 0.8. Now let's see the options. Option A, 50.5% of rated current is the wrong answer. 64% is wrong answer. This is not 64 percentage. Square root of 64 by 100. Nothing but 8 by 10. Nothing but 0.8 is our answer, not 64 percentage. So this is also wrong answer. Don't do the mistakes. And 80%. This is 100% correct answer. 80% of rated current. Nothing but 80% of load. We can get the maximum efficiency. This is simple, very, very easy question. We discussed every formula in the concepts, right? See, for a specified input voltage and frequency, if the equivalent radius of the core of a transformer is reduced by half, the radius reduced by half, the factor by which the number of turns in the primary should change, to maintain the same no load current, nothing but here, to maintain the same no load current and to maintain the same EMF also. EMF also should be same. No load current and EMF both are same. So let's see what is the formula for EMF. E is equals to 4.44 phi m F and N, but generally phi is equals to mmf by S. MMF is nothing but N into I. S nothing but L by mu A. So phi is nothing but Ni mu A by L. That is the phi. So substitute here. E is equals to 4.44 and frequency F and N, number of turns N, and phi is nothing but number of turns into I into mu A by L. Nothing but E is equals to 4.44 into F, because specified frequency, this is N square I mu by L, and A, area. What is the area? In generally we have to take pi r square is my area. Now tell me, now what is the question? Here the radius of the core reduced by half. The radius of this core reduced by half. To maintain the same EMF and same no load current, what is the change in number of turns? See here, the number of turns and radius is inversely proportional to each other. Yes or no? If one decreases, other one should increase. If one increases, other one should decrease. Because these are in multiplication. Then only this value is a constant. Here, if the radius reduced by half, then to maintain same EMF, the number of turns should be double. If radius half, because of square, both are square only. So if radius reduced by half, then to maintain same no load current, the number of turns in the primary should increase to double, then only it should be possible. So what is the answer? 1/4 wrong answer, 1/2 wrong answer. Doubled is the correct answer. Because here the number of turns square is inversely proportional to radius. If this is reduced to half, then this is increased to double. This is generally very simple question. Here number of turns are doubled. Then only we can get the same no load current. Are you okay? In this video, see this question. Assuming an ideal transformer, this is the ideal transformer, the Thevenin's equivalent voltage and impedance as seen from the terminal X and Y, as seen from the terminal X and Y for shown below circuit. For this circuit, they want Thevenin's equivalent to voltage and impedance. Nothing but these two seen from these terminals. Nothing but, for example, this is R1 and this is E1. We have to seen from this terminal nothing but R1 dash and E1 dash. We need these two. What is R1 dash here? R1 dash is equal to, we know, R1 into K square. R1 is the 1 and K. What is K? N2 by N1. K square nothing but 2 square. So the answer is 4 ohms. R1 dash is 4 ohms. This is the answer, 4 ohms. And E1 dash is equals to K into E1. That is K is the 2 and E1 is the sine omega t. K into E1, 2 into sine omega t. Of course, this is your answer. So option A is the correct answer for this question. Very simple. The equivalent seen from the X and Y terminals. X and Y terminals. Seen from this X and Y terminals, nothing but these are from here. Nothing but R1 dash and E1 dash. You have to calculate R1 dash and E1 dash. Then you can get the answer clearly. This is about the equivalent, Thevenin's equivalent circuit question based on transformer. Understood? In this video, the problem on auto transformer, which is very important for competitive exams. Let's see here. A single phase 50 kVA 1000 by 100 volts. Single phase 50 kVA 1000 by 100 volts. Two winding transformer is connected as auto transformer as shown in figure. Like this. See, this is the 1000 volts winding and this is the 100 volts winding. These two are connected. See, this is the dot notations. For example, current is like this. If the current is like this, tell me, this is leaving from the coil and here also leaving from the coil. Both are leaving nothing but additive polarity. Additive polarity. That's why here 1100 volts they given that. Now they are asking what is the rating of auto transformer. This is additive polarity, that's why we can use formula. What is the formula? KVA rating of auto transformer is equals to 1 by 1 minus K times of KVA rating of two winding transformer. 1 by 1 minus K times of KVA rating of two winding transformer. Let's see. 1 by 1 minus K. What is K for our transformer? K is equals to LV by HV. LV by HV. Nothing but 10 by 11. And two winding transformer KVA rating is 50. So what is the answer? 11 by 1 of 50. So the answer is 550 kVA. 550 kVA. This is the rating of auto transformer. This is the one method. I given you three methods. Yes or no? We already done one example problem. Of course, the same voltage problem. For example, the third method, shortcut method. See here, for the shortcut method, 1000 by 100 volts transformer, KVA rating is 50. But now my transformer is 1000 by 1100. Then what is the KVA rating? This is a shortcut method. These two are same, leave them. So for 150, for 1100, calculate 1100 of 50 out of 100 gets cancelled. 1150 is a 550. 550 kVA is your answer. You can do directly. Like this, you can get the answer directly. Auto transformer is very easy. 100% question for competitive exams. Right? This is the question on auto transformer. Right. In this video, let's see the question. The self-inductances of the primary winding of a single phase 50H transformer is 800 millihenry, and the secondary winding is 600 millihenry. The primary winding and secondary winding self-inductances they given. The mutual inductance between two windings also they given 480 millihenry, L1, L2 and M. The secondary winding of this transformer is shorted and the primary winding connected to a single phase sinusoidal voltage source. The current flowing in the both the winding can be neglected. The current is neglected in the both the windings. In this condition, what is the effective inductance? They want the effective inductance seen by the source. Effective inductance seen by the source. This is the question. What they given? They given L1. L1 is equals to 800 millihenry. L2 is equals to 600 millihenry. Mutual inductance is equals to 480 millihenry. This is the given. And here we need a one parameter A is equals to E1 by E2. If they are not given, A is equals to 1. Take this as a 1. So this is the circuit. Now we have to draw the inductance circuit of the transformer. The inductance circuit of the transformer is like this. See, this is a primary and this is secondary. Of course, this is mutual. This is actually the circuit. Here the secondary is shorted. Actually here AV2. This AV2 is shorted, that is 0. And this is the mutual inductance. It should be taken as AM. And here primary is connected to supply voltage with 50H supply. And this primary winding inductance is L1 minus AM. And the secondary winding inductance is A square into L2 minus AM. Remember these words, then you can get the answer. We have a big theory for these words. Just remember these words. Here A, V2, AM, mutual, and primary and the secondary. Secondary is shorted, primary connected to supply. Now we need the effective inductance from the supply, from the source, seen by the source. So calculate, sir. A is the 1 and M is the 480. This is 480. And here L1 is the 800 minus AM is the 480. What is the value? 800 minus 480 is equals to 320 millihenries. This is 480 millihenries. And this one, A square is the 1. A square L2 minus AM is the 480. So 600 minus 480 is nothing but 120. 120 millihenry and 480 millihenries are in parallel, and that too in series to 320 millihenry. So what is the circuit here? This is 320 millihenry and these two are in parallel. When these two are in parallel, its equivalent value is this. What is the equivalent value? We have to calculate. So tell me, what is the L1, L2 by? What is the value when these two are in parallel? 480 multiplied with 120 by 480 plus 120. 480 plus 120 is nothing but 600. 120 ones, 125s are. Alright, 480 by 5. 480 by 5 nothing but 5 ones, 5 eights, 5 nines, 5 nines, 45, 45, 36. So here the answer is 96 millihenries. 96 millihenries. Then what is the effective inductance? What is the effective inductance? The L effective. Effective inductance. The effective inductance is equals to, these two are in series. 320 plus 96. 320 plus 96 is 416 millihenries. 416 millihenries. Is there any answer? Yeah, exactly. We have an answer of 416. Option A only. Option A only. 416 millihenries is our answer. Here the thing you have to remember, L1 minus AM, A square into L2 minus AM, and AV2. Here is the V1 and that is the AV2. You should remember these words. 1, 2, 3, 4. You should remember, then you can get the answer directly. Is it okay? Understood? Question is very, very big question, but answer is very simple if you know these words. If you know this circuit. Right. See, an ideal transformer has an inductive load. Inductive load element at port 2. Inductive load element at port 2 as shown in figure below. The equivalent inductance at port 1. Nothing but, for example, this is Z. Z2. Z2 is equals to L. But I want that equivalent inductance seen from the port 1. Nothing but I want Z2 dash. Z2 dash is equals to Z2 by K square. Z2 dash is equals to Z2 by K square. We know that. What is K? K is equals to N2 by N1. K is equals to N2 by N1. K is equals to 1 by N. Now calculate it. What is Z2 dash? Z2 dash nothing but Z2 by K square nothing but 1 by N square. So the equivalent inductance from port 1 is N square into L. The equivalent inductance from port 1 is N square into L. N square into L is there. Option B. Option B is there. Actually here L, when it comes to from port 1, that is nothing but if it is Z2, you want Z2 dash, Z2 by K square, where K is equal to 1 by N, then you can get N square into L. This is simply the question on equivalent circuit. Okay? Understood? In this video, a problem on hysteresis and eddy current losses. Let's see. A 220 by 440 volts, 50 Hz, single phase transformer operates on 220 volts 40 Hz supply with primary winding. 220 volts 40 Hz supply with primary winding. Then eddy current losses and hysteresis losses decreases, or eddy current losses and hysteresis losses increases, or hysteresis losses increases and eddy current losses remain same, or hysteresis losses remain same and hysteresis losses remain same and eddy current losses decreases and eddy current losses decreases. This is the question they given and options. Let's see. Actually the voltage is 220 volts and the frequency is 50 Hz. But now the transformer is connected to 220 volts 40 Hz supply. 220 volts 40 Hz supply. So first of all, V by F ratio, we have to find out V by F ratio. See here, this V by F ratio is not equals to this V by F ratio. 220 by 50 always not equals to 220 by 40, it's true. So here V by F ratio is not constant. V by F ratio is not constant. If V by F ratio not constant, hysteresis losses directly proportional to V power 1.6 by F power 0.6. This is already I given you, I said you, this is very, very important. So tell me, what happened here? From here to here, the frequency decreases. From here to here, the frequency decreases. When the frequency decreases, automatically hysteresis losses increases. When the frequency decreases, automatically hysteresis losses increases. Where the voltage is constant, there is no change in voltage. Voltage is constant. So here the answer is hysteresis losses increases. Hysteresis losses increases. See, this is wrong answer. This may be right answer. This may be right answer. And this is wrong answer. Now we have two options. And let's go for second one. What is that? Eddy current losses. When V by F ratio not constant, eddy current losses directly proportional to V square. Sir, V square, right? Here, the voltage, there is no changes in voltages. If voltage is constant, then automatically eddy current losses also constant. If voltage is constant, then eddy current losses also constant. So here, see, here eddy current losses increases. Wrong answer. Here hysteresis losses increases and eddy current losses remain same. This is 100% correct answer for the given question. In given question, the eddy current losses are directly proportional to V square. Where V is constant, eddy current loss also constant. This is our answer. Did you understood? This is very, very, very important for competitive exams. Right? See. In this video, see the problem. A voltage V is equals to 400 sine omega t, omega nothing but 3.14.160, is applied to a single phase transformer at no load, on no load. If the no load current of the transformer is given, the magnetizing branch impedance approximately, they want that. So they given voltage and current, just we need to V by I, impedance, the magnetizing branch impedance, Z is equals to V by I. What is V here? V is equals to Vm into sine omega t. I is equals to Im into sine omega t. So we have to consider RMS value, but these two are the maximum values. So what is RMS value? The RMS value of V is equals to maximum by root 2. V by I. I is the 2 by root 2. This is at an angle 0, but this is at an angle minus 85 degrees. This is at an angle minus 85 degrees. So what is the answer? Root 2 gets cancelled. 2 ones are 2, 200s are. And at an angle, this is minus 85. When comes to numerator, plus 85 degrees. 200 at an angle 85 degrees. We have two options. But this is correct answer because this is plus 85 degrees only. Not minus 85 degrees. This is plus 85 degrees. V by I. 400 by root 2, 2 by root 2. 0 minus 85. 200 at an angle 85 degrees. Are you okay? In this video, see the question on open delta connection. Let's see here. A three-phase transformer bank consists of three identical 2300 by 230 volts 15 kVA single-phase transformers which are connected in delta-delta. The bank supplies a 20 kVA unity power factor 3-phase load. 20 kVA unity power factor 3-phase load. If any one of the transformer develops a fault, out of 3 transformers, any one transformer develops a fault and is removed due to fault, the transformer is removed. In delta delta, one transformer is removed, that is called as open delta, we know that. The load carried by each of the 2 transformers now operating in open delta will be dash kVA. What they are asking here? Here they taken 3 transformers, each of 15 kVA, connected in delta delta. But due to some fault occurs in any one transformer, out of 3, one transformer develops a fault, then that transformer is removed. Now we have only 2 transformers, each 15 kVA, which are operating under unity power factor and which are operating under open delta. Can you tell me what is the load kVA for this open delta? The kVA for this open delta, the kVA up to root 3 times of 15, nothing but 1.732 times of 15, 1.732 times of 15. Nothing but we can apply load approximately 15 plus 15 sevens are around 10 plus. Nothing but around 20.6 kVA up to, we can apply the load up to around 20.6 kVA. We can apply. This is the capability of this open delta system. But he said that it is the bank supplies a 20 kVA unity power factor 3-phase load. How much? It is supplies a 20 kVA unity power factor, 20 kVA 3-phase unity power factor load, only 20 kVA load applied on this system. 20 kVA load applied on this system. No need to this is, of course, generally the capability 20.6. But we are applying only 20 kVA. No problem with load. Overload, there is no any overload chances. So 20 kVA applied. Now what they are asking? The load carried by each transformer, now operating in open delta. What is the load carried by the each transformer? Then the load carried by the each transformer is 10 kVA. 10 plus 10 is equals to 20. That's why each transformer carries a load of 10 kVA. There is no any controversy in this question. This is very simple question. Yes or no? Right? In open delta, operating in open delta, each of 15 kVA actually, but we are applying a load of 20 kVA only. So 20 kVA, that's why this 20 kVA shared by 2 transformers equally, that is 10 kVA each. Very simple question. Right? Thank you.